Given a permutation, we can create a graph in the following way. For each element, we add an edge from it to the closest position to its right with a value greater than it, and the closest position to its left with a value greater than it. If the graph that's created by this ends up having a cycle, the permutation is a cyclic permutation. In this permutation, there's a cycle from 3 to 1 to 2 and then back to 3. For a given integer n, we need to count the number of cyclic permutations of length n. Let's split all permutations of length n into two types, unimodal and non-unimodal permutations. A unimodal permutation is a permutation that's increasing up to a certain position, following which it's decreasing. All other permutations are non-unimodal. Let's analyze non-unimodal permutations first. All subarrays of a non-unimodal permutation will look like this. You'll have three positions, I, j, and k, such that p of j is less than p of I, p of j is less than p of k, everything in between positions I and j is less than p of j, everything in between positions j and k is less than p of j. If we were to visualize the graph that forms from this, there'd be an edge from p of j to p of I and p of j to p of k, as those are the closest elements to position j with a value greater than p of j. Now, without loss of generality, we can assume that p of I is less than p of k. As a result, there's an edge between positions I and k. This leads to a cycle of length 3. Hence, all non-unimodal permutations have cycles of length 3. Now let's look at unimodal permutations. Let p of j denote the maximum element in the permutation. All elements from position 1 to position j will be increasing. Therefore, there's going to be an edge from p of I to p of I plus 1 for all I that's greater than equal to 1 and less than j. All elements from position j to position n will be decreasing. Hence, there's going to be an edge from p of I to p of I minus 1 for all I that's greater than j and less than equal to n. This ends up forming a tree, hence it's acyclic. From this, we can conclude that the number of cyclic permutations is equal to the total number of permutations minus the total number of unimodal permutations. The total number of permutations is just n factorial. Let's try and figure out what the total number of unimodal permutations is. Let's try constructing a unimodal permutation of length n on an infinite array. We can arbitrarily place n anywhere we want. Then there are exactly two positions at which n-1 can be placed, either to the left or to the right of n. Let's assume that it goes to the right. Now n-2 can be placed either to the left of n or to the right of n-1. This continues for all elements down to 1, which can again be placed either to the right or to the left. We can see that we have two choices for each element except n. The largest element, where we have only one choice as the entire permutation gets constructed around it. So the number of unimodal permutations of length n is 2 to the power of n-1. Therefore, the total number of cyclic permutations of length n is n factorial minus 2 to the power of n-1. So that's how you solve problem C. I have video editorials for A, B, D and E too, so if you're interested, please check them out. If you found this helpful, please subscribe to my channel. I'm not quite sure what kinds of videos I'm going to make yet, but I do think that 3 Blue 1 Brown style competitive programming videos would be helpful. Please like, share and comment, and feel free to share any suggestions that you might have.